So we've been talking about principal component analysis. I've been trying to emphasize the similarity between the sort of maths we were using and the maths for Bayesian linear regression. And last time we got as far as computing the marginal likelihood for principal component analysis. So the marginal likelihood had a particular form, which was a Gaussian with a mean. So the marginal likelihood of the data given the weight matrix and the noise and the mean. So it's, oh, sorry, yeah, that would be good, thanks. Is independent across data points. What we looked at last time was just for one data point, and because we're making assumptions about, I think I'm using capital N's, aren't I? Since we're making assumptions about independence across data points for both the likelihood and the prior, the overall marginal likelihood is independent across data points. And it has this form, which we derived last time. So p over 2, where p is the dimensionality of the vector ti, which is the ith data point. Determinant of c to the half, and then just a Gaussian form. Where c has this form. This is the bit that we worked out using the matrix inversion lemma and manipulation of the quadratic form. So importantly, we need to find out these parameters. Can you see that? Just about. I'll get the handout. We need to find out these parameters, W, sigma squared, and mu. We can do maximum likelihood to find those parameters. And the answer for mu is the same as the standard answer for maximum likelihood in a Gaussian. So you've got that in your tutorial sheet. How many of you had a go at the tutorial sheet 3 so far? Anyone? Let's see. It's been ages putting these things together to make sure it's there. Everyone just ignores it. Okay, so tutorial sheet 3 has maximum likelihood of this Gaussian form with respect to the covariance c and mu. But the covariance there doesn't have this constrained form, which is a different maximum likelihood. But it turns out that it doesn't matter what the covariance is. The maximum likelihood solution for mu is just the mean of the data. So the mean, as it were. That can sometimes be confusing because this is called the sample mean and this is the maximum likelihood solution for the Gaussian mean. They happen to be the same, so that's why everyone calls everything the mean. This is the mean of the Gaussian. It's a location parameter of the Gaussian as well, and it's the sample mean. Now, the maximum likelihood solution for W is slightly different. So remember we've been talking about in the past Gaussian distributions which are correlated. And the way I introduced that was by saying, if you've got a Gaussian, say maybe over 2 variables, perhaps weight and height, if they're independent, the Gaussian is what? we call axis aligned. So the dominant directions of this oval, what I'm drawing is the contours of the oval. Okay? The dominant direction of this oval is aligned with the axis, this direction here, and then the second dimension in that way. Now, that's for independent Gaussians. So this would be for Gaussians which have a sort of diagonal form. So sort of something along the lines of sigma w squared, sigma h squared, and 0 cross covariance. So I think of that as the cross variance. That's the variance, the covariance between the weight and the height. So that's the independent model. And then for a dependent Gaussian, you rotate it. So to form the rotation, well, let's look at it this way. So think of this axis here. Let's get a good color. This is sigma w. This is sigma h. Yeah? So that's the standard deviation. And where they're showing you the contour on a normal Gaussian, we might have a sort of plot like this, and then a mean, and then sigma w will be somewhere up here, if this is the standard deviation. Yeah? In the two-dimensional Gaussian, these standard deviations are showing you what the principal axis of this contour I'm trying to draw. I'm sort of always pretending I'm drawing the contour at this level, this one standard deviation level here. So the contour is like a ring, it's like that level there, but this is a two-dimensional shape, so I'm just drawing the contour. So whenever I draw it, that's how I imagine it. So sigma w and sigma h are specifying the ellipse that we're drawing. Now, they're axis aligned, but here they're rotated. So you can apply a rotation matrix to these two values, and if we denote that rotation matrix R, so if we have sigma w, notice it's not in the squared form, sigma w, sigma h, and then we rotate by a set of vectors here. Now that leads to a new matrix which isn't necessarily going to be symmetric or anything. So of course this is the standard deviation. We're representing standard deviation. So the result of this is basically two vectors. Having got the rotation, that gives us these two new vectors here. So we get one with x and y in that direction, and one with x and y in that direction. So that gives us this gives us something where you've got elements in each place, just calling them A, B, C, and D. You know, C and B are now non-zero because of the rotation. And what that specifies is these two directions in which you're pointing. Now, the key point about this is a physical representation of eigenvalues and eigenvectors. So the eigenvalues are the length of these things. So you can't see the mouse, sorry. The eigenvalues are the length of these vectors. And the position which they're pointing, the normalized position which they're pointing, is given by the eigenvectors, which are R. So R gives you two normalized vectors. Let's a different color. So R would give you two normalized. The rotation matrix is the normalized the normalized vectors, and then those two guys here, you can see the white, can you? Scale those eigenvectors and turn them into the full length thing. Is that making sense? So the operation, if you've done computer graphics, right, and you can think about this, you should be able to think about this in two dimensions, because this is a rotation matrix here. So in computer graphics, I can't remember how you define a rotation matrix, but it has various cosines and sines based on the angle of rotation. And the angle of rotation is about the axis coming out of the screen, yeah? Now, as you go into higher dimensions, the same thing is true, but you're doing it in a harder way to visualize. You're applying rotation matrices in higher dimensions, 45 dimensions, 100 dimensions. And the things that make up the rotation matrix, again, are the eigenvalues and the eigenvectors. But this isn't a covariance matrix itself because it's sigma W times sigma H. So what we actually have as the covariance matrix, and I have an explanation for this. I've not tried it out on students, so maybe it's just confusing. So be prepared to delete what I'm about to say from your head. Important property of eigenvalue decomposition. Okay, step back a bit. So the determinant, how is it related to the eigenvalue? So we've been using determinants a lot. So we've been talking about determinant of C to the half. That's been appearing always in the normalization. I just want to give you the reason why that keeps popping up without showing the details. So the determinant of any matrix is the product of the eigenvalues. So the eigenvalues in this case are the standard deviations in the aligned case. Now let me show you why that's really obviously going to be the case. So, or why that's going to be important. What is, this is a question my son can answer, so I hope you guys can answer that. What is the area of this square? Yeah, so sigma W times sigma H multiplied together. Okay? So what's the volume if we add an additional one? Just multiplied again. So think of this representation I'm sort of showing you of the independent Gaussians. So sigma W, sigma H, sigma something else, going across the diagonal. If you take the product of all those things, you get a volume, which is the volume of the rectangle they're prescribing. Now, when you're normalizing the Gaussian, it's come from integrating across the Gaussian. You don't get this term exactly, this sigma, 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 because you're not measuring the volume of this square. You're measuring a different volume, yeah? But you can see that there's going to be a term that should be related to that. Now, there's something funny about this, because I drew that in a particular way. What happens if I change the direction of sigma H? What will the volume now be if I just multiply all these guys together? Be negative. So negative volumes don't make any sense. How do you deal with negative volumes? Absolute them. So how do you absolute something? You square it and take its square root. So think about what's going on up here. The determinant we actually have is the determinant of C to the half. C is not the set of axes. C is a result of R, or put the R, transpose at the end, R times these set of axes squared times R. Yeah? And then it's square rooted. So what's actually going on in that term, the reason it's the covariance isn't these directions. The covariance is the square of these directions because these directions are, in effect, the standard deviations. Yeah? So these principal axes I'm showing you associated with this Gaussian, that's sort of like equivalent to the standard deviation in the univariate case. We don't, and that is represented by the eigenvectors of the covariance. Why is it represented by the eigenvectors? Well, if you square this whole beast that we've been talking about, so you can square it by going, so the thing we've been talking about is take these two axes here and then rotate. But when you square it, you don't square it by multiplying by the same thing again, you square it by multiplying by that thing transpose, yeah? So pre-multiplying by that thing transpose. So you end up with something of the form R sigma squared W 0, 0 sigma H squared R transpose, which then matches, so in effect you rotate either side. Why does that come out? Well, if you look at these quadratic forms, which keep appearing everywhere, you've got things in this form, t minus mu, c minus 1, t minus mu. Like this, these things appear everywhere. Now the cool thing about that representation for R, so I'm just going to call this thing in the middle D, this diagonal matrix like this, that's C. C inverse is just given by R D minus 1 R transpose. Why is that? Because by definition, R transpose R is equal to I, because it's a rotation matrix. Yes, because a rotation matrix, remember, if you apply a rotation matrix and then you apply the rotation matrix transpose, you're just reversing the rotation. So the final result is simply stay where you are. And the stay where you are matrix is the identity matrix. So what this is saying, if you substitute that in here, and another way of looking at everything is R D minus 1 R transpose T minus mu. By the way, this is all understanding. I'm not trying to, this is trying to teach you to understand eigenvalues and eigenvectors. I want you to listen and understand this. I'm not going to ask you to sort of reproduce each detail of what I'm giving you. I'm trying to give you the understanding of physically what an eigenvalue and an eigenvector is. So what's going on here is you can view this, so we've been talking about this as a rotation applied to the variances, and this is a rotation applied to the standard deviations. These two things as rotations applied to the standard deviation. But here's another way of looking at it. What about its rotations applied to the data points, or the centered data points? So ignoring the centering here, take the mean off before you apply the rotation. Now apply the rotation to the data point and model it with an axis-aligned Gaussian. The two representations are completely equivalent. Yeah? So what you can see is this decomposition of the covariance from a full covariance positive definite matrix down to a diagonal matrix is just rotating the axes in which you're working. So those rotations are telling you the directions of most correlation. Now, why is all that important? Well, it turns out that the solution for W is given by these R's. Not all of the R's, because R is a P by P matrix. And W is P by Q. So it's given by the eigenvectors of the covariance matrix that are associated with the largest directions of variance. Okay, so what I've been saying, so you compute the sample covariance. So the sample-based covariance for the data is the solution. If you were just fitting C directly, and this is in the tutorial sheet. This is why I gave out the tutorial sheet, so you would all be on top of this. So where this is the sample-based mean, the covariance of your data set is given by this. It's just the covariance of your data. W is given by taking C, computing its eigenvalue decomposition. So we've been using R. Actually, I'm going to regret using R. So the eigenvalue decomposition of oh, wow. I don't think I've done that before. Oh, wrong way. Let me save this. So what is the eigenvalue decomposition? The eigenvalue decomposition is defined, well, in fact, since we're here, why don't we just see what Wikipedia says on the subject? Since you'll all be checking that anyway. Now, I think they'll probably write it in vector form. So the eigenvalue decomposition of this matrix A is that matrix times its eigenvectors is equal to the eigenvalue times the eigenvectors. So they've written it in a scalar form, which I don't like to do. I like to write it in the matrix form. And it's got various properties going on and on and on and on. Here's one of them. The determinant is equal to the product of the eigenvalues. So that's important. That's what I was sort of hinting at with the space there. I mean, they are crucial objects, but I think sometimes it's hard to get a physical understanding of what the object is. I like to think about them as these principal directions for positive definite matrices. This is these principal directions in the Gaussian covariance. So this is the matrix way of writing down the eigenvalue decomposition, where lambda are the eigenvalues and r are the eigenvectors. So why is this true? Well, if I so what does this mean for us? If I post-multiply this by R transpose, now, because R is a full rotation matrix, R transpose R is I, but R transpose is also I, because that's applying the reverse in rotation, and then I'm doing it again. So if I post-multiply this by R transpose, I get this. Okay? So be careful, because these guys here are actually the square of what we've been talking about, yeah? Not the square root. They're not the, because we're dealing with this object squared, what we recover here is the variances, those axis-aligned variances, not the axis-aligned standard deviations. Because this is the maximum likelihood fit for the covariance, and what this is saying is that eigenvalue decomposition, this is what I've been writing before, yeah? And you can see how that's relating to this equation here. This is how you define an eigenvalue decomposition. You're looking for an orthonormal matrix, a rotation matrix, R, such that this is true. And there are algorithms for doing this. There are algorithms that it's all in Octave, it's in Python, it's in everything. Yeah? So you can just recover these results. The complexity of the algorithm is cubic in the dimension of C. So it turns out that the solution for W is to extract the first Q eigenvectors associated with the largest Q eigenvalues. Yeah? And I'm not proving this. It's going to be in the slides I'll show later, because it's part of the talks I sometimes give just as background. I'm not proving this here. Multiplied by, if this lambda is the square root of lambda minus sigma squared, where sigma squared is the noise variance to the half. So bear in mind that lambda is the eigenvalues, the variance is in those axis-aligned directions. What is this saying physically? Well, it's hard to sort of talk about really in two dimensions, but what it's saying is that W, if Q is 1 and P is 2, so this is a direct example where P is 2 and Q is 1, what this says is the principal eigenvector, in this case, the one principal eigenvector is that one, yeah? The dominant eigenvector is that, and W is given by that eigenvector times its associated eigenvalue minus the noise squared to the square root. Now, principal component analysis defines W to just be this. Pure principal component analysis. So the only difference is the noise. So if you take the noise to 0, The two are completely equivalent. If the noise is non-zero, what the noise is then required to do is explain the off-diagonal variance. The fact that the data isn't coming from this line. It's coming from off the line. So it's like, what it's saying is, okay, let's think about what this is meaning physically. It's saying that your data is generated by sampling from a one-dimensional Gaussian in X. Yeah? So we get some samples from here. These are our latent values X, one-dimensional. We then multiply by W. So this is X, and we multiply by W. W, we know, is the dominant eigenvalue, and it's a rotation times a scale. So the rotation takes what was X along this axis here, rotates it along here, and scales it. So it takes these guys here, and effectively it plots them in 2 dimensions along a line here. Yeah? That's the operation. The prior over X was Gaussian, univariate. We rotate the prior over we rotate the outputs from X. They move into a dimension here, and then we scale them by lambda. This is what the multiplication by W does. So the scaling by lambda moves them in or out in that direction. So that's part of our likelihood. Our likelihood was Xi our likelihood, I'm now writing the wrong way around, is W Xi plus noise and plus a mean. Ignoring the mean for the moment, assume everything's centered, so ignore the mean, plus noise. So the noise, the variance of the noise is sigma squared in all directions. Yeah? So once you've, it's not just in one direction, once you've got it in this point here, then the data actually is moved away from the line by a little bit of unidirectional noise. So look at the scaling. The scaling has to subtract that noise off. Yeah? Or else the scaling would be wrong. Because the noise is added after you apply this matrix W. And in the directions you didn't find the principal components, the noise is giving the rest of the distribution. So in fact, a two-dimensional Gaussian like this, you can represent with one principal component plus noise. Turns out, as you go into higher dimensions, what's actually going on is you will actually be approximating. So if you have one principal component in high dimensions, you have to think of like a Gaussian sausage. So it's a sausage, what it defines in higher dimensions, say in 3 dimensions, is a single direction, like the direction I'm pointing in at the moment, plus noise coming away from it. So that's a 3-dimensional Gaussian based on one principal component. So in other words, based on W transpose, where W is P by Q, where Q is 1 now. Yeah? So that's a rank 1. That's one principal component in the model. As you increase the principal components in the model, in 2 dimensions, that becomes, potentially a sort of flat pancake shape, an ellipse, which I can't really draw very well. I mean, I have to draw it in, I have to try and my 3D drawing skills. It's something like this in 3 dimensions, yeah? But 2 of these dimensions are specified, and the remaining dimension is the noise. But if we add more and more dimensions, all those extra dimensions are just noise. So you're looking for the dominant directions of your data. It turns out that what principal component analysis does is, if you've got some sort of data, and it's not always Gaussian, obviously, it looks for the dominant direction, W. And that's found by the eigenvectors and the eigenvalue. The pointing direction is the eigenvectors, and the length of the pointing direction is the eigenvalues of the covariance, the sample covariance of the data. So the lesson is that PCA, you can find the PCA solution. PCA is solved by the eigenvalue problem on the data covariance. It's a really simple operation. I mean, one of my PhD students said to me once, he'd been to a meeting across the other departments in the engineering faculty, And he'd seen a load of talks about what they were doing, and he said, you know, it seems to me that every PhD project in the entire faculty is just people applying PCA to some engineering data. Okay, maybe that was an oversimplification. But it sometimes does feel like that. It's not a complex operation. It's something easy to do. It's also known as, is it the I can't remember. Kahunen Löw transform. That's what it was. It was developed independently in engineering. It was developed independently by Pearson. Pearson was a statistician. I like the Hotelling derivation. He named it as well. Pearson was interested in the fact that if you do a linear regression, so just as a bit of history, if I do a linear regression and I do a line fit to some data here, I get a line out, yeah? And Pearson pointed out, but if I reverse, this is how Pearson motivated himself, if I try and regress t onto x, which is a one-dimensional thing, I get another line out. It's not the same line. If I reverse these two things, it's not the same line. And Pearson said, if I want to be able to reverse these two things, what line should I be looking for? And the answer again is principal component analysis. Find the direction. So now we've been thinking of this data as input and output, but now it's just 2 dimensions. And if it's just a little Gaussian cluster like that, then the principal component is the line you need to extract. And that's why people say Pearson derived it in 1900 or whatever. But he was actually asking a slightly different question to the one we were asking. So our latent variable is always operating across this line, basically. What we're doing is we're decomposing this Gaussian into our latent variable living along this line, which is being moved around. Now, does that make sense? So I'm not proving this solution, but I want you to understand the physical intuition behind the solution for PCA. Yeah? The proof is in the Journal of the Royal Statistical Society, Series B, by Tipping and Bishop in 1999. Okay? And it's called Probabilistic Principal Component Analysis. And what they also show is when you do an eigenvalue decomposition of any covariance matrix, people love plotting the eigenvalues. So if you order the eigenvalues largest first, you know, as you go, as you think about these Gaussian balls, they're not always Gaussian balls, obviously, the data, but that's what you're fitting to your data. They have all these different dimensions, and what people will then plot is plot the dominant one first. Here's the first eigenvalue, here's the second, here's the third, fourth, fifth, sixth, seventh, like this. And they'll tend to tail off. It's very common that they do this. So if you say q is equal to 2, that's the model parameter that you fix. The dimensionality of your model finishes here. Q is equal to 2. Well, it turns out the solution for sigma squared is to average the remaining ones you discard. That's the maximum likelihood solution. It's to average the things you discard. So wherever you set q, if you set q to 4, then the average is the remaining ones you discard. That, of course, ensures that since the discarded ones are always smaller, the smallest ones, sorry, I should have had a q in here. This is the first q principal eigenvalues. So that is a diagonal matrix made up of these eigenvalues here. And since that's the average of the discarded ones, obviously sigma squared is always going to be smaller than lambda q, and you don't end up with negative things to square root inside here. Yeah? Interestingly, if you do it the other way around, if you fix sigma squared beforehand, you say this is the noise level, you know the noise level, then that will tell you how many eigenvalues to discard. So you can think of sigma squared as living on this axis, because this is lambda, is in the same scale, they're both variances. Right, one's a variance which is giving you the axis things, and the other's a circular variance. So if you set sigma squared at some level, then the maximum likelihood solution says you must discard all those. It tells you the cutoff of what the dimensionality is. So we've used this in some of our own work where we've done microarray analysis, and we try and extract sigma squared as part of the analysis, and then we know the dimensionality of PCA to use. So that's a nice little trick that we've done there. So this is linear dimensionality reduction, and I haven't shown you, you poor things, any pictures of the sort of results you get. So what can you do with this? Once you've got W, you can ask the question of, remember we derived a while ago now, what is the probability of x, I, given W and Ti and sigma squared? Yeah? So you can get a mean and covariance for that. So you can visualize the latent variables given your data and your W. So you can compute W, and then you can say, please plot this data back into this low-dimensional space. And that's what I want to do next. And it's going to lead on to... well, let's pause there for a moment and just say, are there any questions about that? Because... by the way, I get really freaked out by these Wikipedia people they put at the top. And the thing is, like, if you pay money, they don't disappear. It just freaks me out. Yeah, it's like, give me the money now. Anyway, so sorry about that. Let's get rid of him. Okay, good. That's better. Are there any questions about what I've been talking about this morning? You know, it's been mostly intuition trying to explain how an eigenvalue decomposition relates to a covariance. Are there any questions about what I've said, bits that didn't make sense?
I've read somewhere that when implementing PCA, sometimes it's more efficient using something called single value decomposition.
Yeah, okay, that's a good question. So the question was, for the benefit of those watching at home, that sometimes you can implement PCA through the single value decomposition. So that's a very good question. Okay, so what does that mean? So the singular value decomposition is another type of decomposition. You can take any matrix, let's call it Y. I hate using T. I'll use Y for the moment. Singular value decomposition is defined as this. Any matrix can be decomposed into two, what I think of as rotation matrix, but they're both what I've been describing as rotation matrix, but you can talk about them as orthogonal matrices. Here's a nasty bit of terminology for you. If a matrix is orthogonal, this is true. But for a vector, for some bizarre reason, two vectors are orthogonal if that's true, and then the vector is said to be orthonormal if that's true. So this is just exploring all that. So this is an orthonormal because it's normal length. It's normalized to 1. But you don't talk, an orthogonal matrix is always normalized to 1. I don't know why. But the term orthogonal means that the vectors in it are orthonormal. You don't have to say it's an orthonormal matrix. But it's let's think of it, I think physically, it's a rotation matrix. It's something that provides a rotation in high dimensions. And both U and V do this. And then the thing in the middle is, again, it's our friend, the diagonal. But now, it's the diagonal, it's the sigma W, sigma H. So this is a good way of representing what we've been talking about. So any matrix can always be represented exactly like that, where the dimensions of this will be... So if Y is n by P, then U is n by n. Now, let's get this right. Actually, I would rather do U is n by P, and S is P by P, and V is P by P. So U isn't necessarily square, but V is. I think you can do it the other way around as well, but this is the way, I'm not certain about that. So that's called a singular value decomposition. Now, probably set this up the wrong way around to what I want to say next. Bugger. Okay, so let's... Okay, we'll do it the other way around with this representation. Sorry. N by n times n by n times n by p. This is n by p. This sum, if y is centered, so if y has its mean removed, then y transpose y, 1 over n, is the covariance matrix. It's just that old thing again, that the sum of y transpose over I can be written in matrix form y transpose y. So what that means is the covariance matrix is given by US V transpose pre-multiplied by VS U transpose. Now you know why I wanted U to be n by n. U transpose U is the identity because it's a rotation matrix. So what you're left with is Vs squared V transpose, which is exactly the same as the R lambda R transpose. So V in our case is R. So the single value decomposition gives you both these things, but when you compute the covariance of the data set, one of those things disappears. So it's another way of computing the principal components. When you do the singular value decomposition, the eigenvectors are given by V, as I've written there. They're directly equivalent. So it's just a different way of computing it. It involves a slightly different algorithm. Whether or not it's more efficient, I'd have to think about that. But people often do it that way. So it's a very valid way of doing it. The thing you have to remember is the singular values are the sigmas, whereas in the eigenvalue decomposition, the eigenvectors are the sigma squared. Yeah? So in effect, the singular value decomposition is even closer to doing what this matrix we were talking about. It's extracting these guys directly and their coordinate system. What does this missing matrix mu do? Well, it actually provides a further rotation. It prevents these being orthogonal. So I haven't gone into this, but what that matrix would do, so I can, what we're getting is an orthogonal basis. The two axes are at right angles. If you then rotate further by that additional matrix U that disappears in the covariance, what you start recovering is all these things. You can actually, W can also be represented by pairs of axes like this. Sorry, let me do a different color for that, green. Or also this. Ignore this if it's not making sense, because it's just a sort of additional background. And PCA just extracts the orthogonal variant. There's one uniquely defined orthogonal variant of axes, but there's an entire rotation of W's. Because if you think about W itself, this is always true for W, that you can put any rotation inside W, another rotation, let's call it U. In fact, it is U in this case. You can always put any rotation inside W, and it will just disappear when you derive this covariance matrix. And that rotation is representing the fact that you can rotate all these eigenvectors around, and they just, as you rotate them, they start becoming non-orthogonal. But you can just kind of ignore that for the purposes of this course and just think about the fact that you get two orthogonal ones. That's the bit in single value decomposition that you're throwing away. Any other questions? Okay. So how do we do this in practice? Well, let's try and okay, so this is last lecture's notes. Oh, I thought I had diagrams on there. Damn. Okay, well, what we'll do, I'll dig out, I want to dig out a few plots of some principal component analysis. But why don't we, since I've got to now find those, we'll break for 10 minutes. So back here at 3 minutes to 10 while I dig out those. Not sure what's happened there. Oh, it's because I haven't put the...